Welcome to The Deep Dive, the show where we take a stack of sources and extract the most important nuggets of knowledge to get you well-informed, fast. Today, we're plunging into something that, well, it underpins every single change in the universe. Energy, whether it's the subtle shift when a chemical bond forms or, the dramatic explosion of a car airbag, energy is always involved.
Absolutely. It's sort of the invisible force driving all transformations, both physical and chemical. Think about the food we eat, how power plants generate electricity. Understanding its flow is really fundamental to chemistry.
Right. So our mission today is to take a deep dive into the fascinating world of energy changes and chemical reactions, often called thermochemistry. We're primarily drawing from Chapter 10 of Chemistry, Atoms First, by Julia Burge and Jason Overby. We'll unpack the core ideas of how energy flows, how we measure it, and importantly, what it tells us about the stability of compounds.
Exactly. Think of this as your shortcut to truly grasping the energetic heart of chemistry. We want to help you get those aha moments that make these sometimes complex ideas really click, especially for, students trying to build that foundational understanding.
Okay, let's start by grounding ourselves. In chemistry, when we talk about energy, what are we really focusing on?
Good question. We're often talking about chemical energy. And that's essentially potential energy stored within chemical bonds, the connections holding atoms together.
Okay, potential energy in bonds.
Yeah. And when old bonds break and new ones form during a reaction, that stored potential energy changes. And those changes, well, they show up as heat being either released or absorbed.
And to track this, chemists use a specific framework, right? The system and surroundings.
That's right. It's crucial. The system is the specific part of the universe we're interested in, like the chemicals actually reacting in a flask.
Got it. The reaction itself.
And the surroundings. That's simply everything else around it. The air, the flask, your hand holding the flask.
The rest of the universe, basically.
Pretty much. And the key insight here is that energy transfer always happens between the system and its surroundings. It doesn't just, vanish or pop into existence.
Okay, so if you're melting an ice cube, the ice is the system.
Exactly. The ice is your system. And the air around it, maybe the cup it's in, your hand, if you're holding it, that's all the surroundings absorbing heat from the ice. Wait, no, the ice is absorbing heat from the surroundings.
Right. The surroundings lose heat, the ice gains it. Makes sense.
Precisely. Energy moves between them.
And when we talk about energy moving specifically as thermal energy, there's a specific term we use, isn't there?
Yes, and it's a common point of confusion, actually. Heat is specifically the transfer of thermal energy. It happens between two bodies that are at different temperatures. It's the process of energy movement, not the energy itself.
Okay, heat is the transfer. And this transfer leads to how chemical changes actually feel to us, doesn't it? Like hot or cold.
Exactly. That brings us to exothermic and endothermic processes.
Right. I think we've all felt a test tube get warm or cold during an experiment. What's going on there?
So an exothermic process is one that releases heat. The system gives off heat to the surroundings.
Okay, exit like exit. Heat exits the system.
Perfect way to remember it. And in these reactions, the products always have lower energy than the reactants started with. Think of anything burning that's classic exothermic. The Hindenburg disaster is a very dramatic example of hydrogen combustion releasing massive energy.
And these feel hot because the heat is flowing out towards us, the surroundings.
Precisely. Now, the opposite is an endothermic process.
Endo, like into.
Exactly. It absorbs heat from the surroundings into the system. In this case, the products end up with higher energy than the reactants.
Like melting ice.
Melting ice is a perfect example. It actively pulls heat in from its surroundings. That's why it feels cold. It's drawing heat away from your hand, for instance.
So if something feels cold, it's actually taking heat from you. That really does connect a lot of everyday feelings to the underlying chemistry.
It really does. It's all about the direction of heat flow.
And when we measure this energy, the standard unit is the joule, right?
Yes, the joule J is the SI unit. But we also encounter the calorie. And this is where a lot of students might get confused, especially with food labels.
Ah, yes, the big C calorie versus the little c calorie. Can you clear that up? This seems like a classic misconception spot.
Definitely. It's a great aha moment waiting to happen. The scientific calorie with a lowercase c is the heat needed to raise 1 gram of water by 1 degree Celsius. It's quite small.
Okay, 1 gram, 1 degree C.
Right. But the nutritional calorie with that capital C you see on food packaging is actually a kilocalorie.
1,000 of the small ones.
Exactly.
Yeah.
So 1 calorie nutritional equals 1,000 calories scientific. And that's equivalent to 4,184 joules.
Wow. Okay, so the energy numbers on food labels are actually kilocalories. That's a huge difference.
It is a really important distinction to make. It explains why food energy values seem so large compared to typical lab reaction values sometimes.
That makes sense. So these energy transfers, they follow rules, universal rules. And this brings us to the bigger picture of thermodynamics.
Yeah, well, thermochemistry, which we've mostly been talking about, focuses on the heat changes in chemical reactions. Thermodynamics is broader. It covers the interconversion of all forms of energy, heat, work, potential energy, you name it.
It's like the rule book for energy in the universe.
That's a good way to put it. And a really core concept in this rule book is the idea of a state function.
State functions. Okay, what are those exactly, and why are they so important for understanding energy?
Right. State functions are properties that depend only on the current state of the system. It doesn't matter how the system got to that state.
Okay, path independent.
Exactly. Think about elevation. Imagine you're on the fourth floor of a six-story building. Your change in elevation from the ground floor is fixed, right? Maybe 40 feet. It doesn't matter if you took the elevator straight there or if you climbed the stairs to the sixth floor and then walked back down 2 flights. Your final elevation change compared to the ground is still 40 feet. Elevation is a state function.
Ah, okay. But the effort involved going up and down stairs is definitely more effort than the elevator.
Precisely. The effort or the distance you walked is not a state function. That depends on the path you took.
Got it. So how does this apply to energy?
Well, the key state functions in thermodynamics are things like internal energy, U, pressure, P, volume V, and temperature T. But here's the crucial point. The two ways energy is transferred, heat, Q, and work, W, are not state functions themselves.
Heat and work depend on the path, like the stairs versus the elevator.
Exactly. How much heat is transferred or how much work is done can vary depending on how you carry out the process. But, and this is vital, the total change in the system's internal energy is a state function.
Okay, so Q and W individually depend on the path, but Q plus W does not. It only depends on the start and end states.
You've got it. And that leads us straight into the absolute cornerstone. The first law of thermodynamics.
Which is?
Energy conservation. Energy cannot be created or destroyed, only converted from one form to another. Or, put another way, the total energy of the universe is constant. If a system loses energy, the surroundings must gain that exact amount, and vice versa. U system plus E surroundings equals 0.
Energy just moves around or changes form. It never disappears.
Never. That's the first law.
Okay. So how do we actually track this internal energy change using heat and work? You said U equal Q plus W.
Right. And getting the signs right here is absolutely critical for calculations. It's another spot where folks can easily make a mistake.
Let's clarify those sign conventions then.
Okay. For heat, Q.
Huh?
If heat flows into the system, endothermic, Q is positive. If heat flows out of the system, exothermic, Q is negative.
Okay. Heat in, positive Q. Heat out, negative Q. Makes sense. What about work? W.
For work, W, if work is done on the system like compressing a gas, W is positive. If work is done by the system like a gas expanding, W is negative.
Work done on the system increases its energy, so positive W. Work done by the system uses its energy, so negative W. Got it.
Perfect. And in chemistry, a very common type of work we encounter is pressure volume work, or PV work. This happens when reactions involve gases that expand or contract. The formula is W equals is BV, where P is external pressure and dV is the change in volume.
Can you give us a real-world example of that PV work?
Sure. A really dramatic one is the airbag in your car. The explosive decomposition of sodium azide, NaN3, happens incredibly fast.
Right.
It generates a huge amount of nitrogen gas, N2. That gas rapidly expands, pushing the airbag material outwards against the atmospheric pressure inside the car. That expansion is work being done by the system, the reacting chemicals, and the N2 gas. So W is negative in that case.
Wow. Okay, so the expanding gas does work on the surroundings, inflating the bag. That's a life-saving application of PV work.
It really is.
Okay, so we have internal energy. But often in chemistry, especially in the lab, we talk about enthalpy. What's the difference and why do we need another term?
That's a really practical question. Enthalpy, represented by H, is defined as HNU plus PV. Now, why introduce this? Because most chemical reactions, especially in a teaching lab or an industry, are carried out at constant pressure, usually open to the atmosphere.
Right, not in some sealed, rigid container, usually.
Exactly. And under constant pressure conditions, the heat absorbed or released by the system is equal to the change in enthalpy. So QP equals H.
Ah, okay. So if the pressure isn't changing, the heat flow we measure is the enthalpy change.
That's the key takeaway. Enthal is often called the heat of reaction at constant pressure. It's incredibly useful because it directly relates to the heat we can easily measure in most common experimental setups.
So HH is super practical if H is positive.
Endothermic process. Heat is absorbed by the system.
And if H is negative?
Exothermic process. Heat is released by the system.
Got it. And we often see these ADH values written right alongside the chemical equation itself?
Yes, those are thermochemical equations. They give you the balance reaction and the associated enthalpy change. Extremely useful.
And there are rules for working with these, right? You can't just ignore the H value.
Absolutely not. There are 3 key guidelines. First, physical states matter. Always include G for gas, L for liquid, S for solid, AQ for aqueous. Why? Because changing state involves energy. For example, burning methane to produce gaseous water versus liquid water gives different H values because turning liquid water into steam requires energy.
Okay, states are critical. What else?
Second, scaling. If you multiply the coefficients in the balanced equation by some factor, say, you double the reaction, you must multiply the H value by the same factor. Double the reactants, double the heat exchanged.
Makes sense. More stuff reacting means more energy change. And the third?
Third, reversing reactions. If you flip a reaction around, turn products into reactants, you simply change the sign of H. If melting ice is endothermic, positive H, then freezing water is exothermic, negative H, with the exact same numerical value.
Okay, reverse the reaction, flip the sign of H. Those 3 rules seem really powerful for calculations.
They are. They allow us to use known thermochemical equations to figure out the energy change for amounts not explicitly stated, or for related reactions, like using the photosynthesis equation, which has a known H, to calculate how much solar energy is needed to produce, say, 100 grams of glucose.
This naturally leads us to how we actually measure these heat changes in the lab. That's calorimetry, right?
Exactly. Calorimetry is the science, or maybe the technique, of measuring heat changes, and the device we use is a calorimeter.
Now, before we get to the devices, there are 2 related terms about how substances absorb heat. Specific heat and heat capacity. What's the difference? It sounds like another potential point of confusion.
It can be, but it's straightforward once you see the distinction. Specific heat, often symbolized by AS or spec S, is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius, or 1 Kelvin. Its units are typically joules per gram per degree Celsius, JG degrees.
Okay, specific heat is per gram. It's about the substance itself.
Precisely. It's an intensive property. It doesn't depend on how much stuff you have. Water, for example, has a famously high specific heat, about 4.184 JG degrees C. That's why large bodies of water moderate climates so well, they can absorb a lot of heat without changing temperature drastically.
Right, so what's heat capacity then?
Heat capacity, usually C, is the amount of heat needed to raise the temperature of a specific object by 1 degree Celsius. Its units are just joules per degree Celsius, J degrees C.
So heat capacity is for the whole object, like a specific beaker or a metal block, and it depends on how big it is.
Exactly. It's an extensive property. It depends on the amount of substance. The relationship is simple. The heat capacity of an object C is just its specific heat, S multiplied by its mass, MC equals ism.
Got it. Specific heat is per gram. Heat capacity is for the whole item. So how do we use these in calorimeters? What are the main types?
Well, the simpler type is constant pressure calorimetry. Often this is done using nested styrofoam cups, the classic coffee cup calorimeter.
I remember those from labs.
Yeah. They work surprisingly well for simple experiments. The idea is that the styrofoam provides decent insulation. You run your reaction in the water inside the inner cup, maybe neutralizing an acid with a base. The heat released or absorbed by the reaction changes the water's temperature.
And because it's open to the room, the pressure is constant.
Right. And the key assumption is that any heat lost by the reaction, the system, is gained by the water and the calorimeter itself, the surroundings, or vice versa. So system pre-surroundings. By measuring the temperature change of the water and knowing its mass and specific heat, you can calculate the heat of the reaction, which is AH.
Okay, coffee cup for constant pressure, measuring AH. What's the other type?
That's constant volume calorimetry. This uses a much more robust sealed container called a bomb calorimeter.
This sounds intense.
It's built to withstand high pressures because it's typically used for combustion reactions, which can be quite vigorous. You put your sample inside the sealed bomb, fill it with pure oxygen, and ignite it electrically. The whole bomb sits inside a container of water.
So it's a sealed system, volume can't change.
Exactly. Since 0, 0, no PV work is done, W0. So Any heat released by the combustion reaction is absorbed by the calorimeter, the bomb itself, and the surrounding water calorimeter. It's an isolated system overall, so reaction equals calorimeter.
And in this case, the heat measured, QV, is equal to the change in internal energy, U not A gauge, right? Because the volume is constant.
Precisely. Bomb calorimetry measures U directly. And what's really cool is its direct application to food.
Food again. How so?
This is exactly how they determine the caloric content on nutritional labels. They take a known mass of the food maybe, like a cookie or a chip, put it in the bomb calorimeter, burn it completely, and measure the temperature rise of the water.
Seriously, they just burn a cookie.
Yep. From the temperature change and the known heat capacity of the calorimeter, they calculate the energy released in kilojoules or kilocalories per gram of the food. That's where those numbers on the package come from.
Wow, that's surprisingly direct. It's not just some theoretical calculation.
No, it's based on actually measuring the heat released when the food combusts. A very practical use of thermochemistry.
That's fascinating. Okay, so we can measure heat changes directly with calorimeters. But what if a reaction is, say, really slow, or maybe dangerous, or has unwanted side reactions? What if we can't just stick it in a calorimeter easily?
Now we get to some clever indirect methods. The most powerful is probably Hess's law.
Hess's law. What's the core idea there?
It comes back to enthalpy, H being a state function. Remember, state functions don't depend on the path taken, only the start and end points.
Right, like the elevation example.
Exactly. So Hess's law states that if you can express an overall chemical reaction as the sum of two or more other reactions, the enthalpy change for the overall reaction, Hoferal, is simply the sum of the enthalpy changes for the individual step reactions, H1 plus HH2 plus.
So it doesn't matter if the reaction happens in one big step or a series of smaller steps, the total energy change is the same.
That's it. This is incredibly useful because we can find the H for a reaction we can't measure directly by combining the known H values of other reactions that do add up to our target reaction.
It sounds like putting together a puzzle using known thermochemical equations. You might have to flip some equations around.
Right, which means flipping the sign of their H.
Or multiply an equation by a factor.
Which means multiplying its H by the same factor.
And then you add them all up, and the intermediate substances cancel out, leaving your target reaction and its overall H.
That's the perfect analogy. It's like algebraic manipulation, but with chemical equations and their energy changes. It allows us to calculate enthalpies for reactions that would be very difficult or even impossible to run cleanly in a calorimeter.
Okay, Hess's law is a powerful tool. And related to this, there's the concept of standard enthalpies of formation, right? Providing a sort of reference point.
Yes, exactly. Think about elevation again. We need a reference point, like sea level, which we define as zero elevation. We need something similar for enthalpy because we can't measure absolute enthalpy, only changes.
So what's the sea level for enthalpy?
It's the standard enthalpy of formation, THF degrees. The little circle means standard conditions, and the F means formation. It's defined as the heat change when 1 mole of a compound is formed directly from its constituent elements with everything in its standard state.
Standard state. What does that mean specifically?
Standard state means the most stable form of an element at standard conditions, which are usually defined as 1 atmosphere of pressure and typically 25 degrees Celsius, 298 K. So for oxygen, the standard state is O2 gas. For carbon, it's graphite. For iron, it's solid Fe metal.
Okay, most stable form at 1 attaville and 25 degrees Celsius. And what's the enthalpy of formation for an element in its standard state?
By definition, it's 0. That's our sea level. The enthalpy change to form O2 gas from O2 gas is 0. The HF degrees for graphite is 0.
Got it. So these ACAS degrees values exist for compounds. How do they help us calculate the enthalpy change for any reaction? That seems like the real power here.
It is incredibly powerful. Once you have a table of standard enthalpies of formation, which are widely available, you can calculate the standard enthalpy of reaction for almost any reaction using a straightforward formula.
What's the formula?
It's HFHM equals NHHM equals HFDFAHF for products.
Okay, hold on. Sum of N times delta H of products
Yeah.
minus sum of N times delta H of reactants. What are N and M?
Good clarification. N and M are just the stoichiometric coefficients in the numbers in front of each substance in the balanced chemical equation.
Ah, so you take the sum of the HF degree values for all the product compounds, making sure to multiply each by its coefficient in the balanced equation, and then you subtract the sum of the HF degrees values for all the reactants, again multiplied by their coefficients.
Exactly. Remember that elements in their standard state have IHF degrees OZ, so they often drop out of the calculation unless they are forming a compound.
Wow. So if you have that table of AHF degree values, you can basically calculate the heat released or absorbed for potentially thousands of reactions without ever stepping into the lab.
That's the beauty of it. It leverages Hess's law and the concept of standard states to provide a universal way to determine reaction enthalpies. It's a massive shortcut and a fundamental tool in chemistry.
That really is a cornerstone concept.
Yeah.
Okay, let's shift slightly and delve a bit deeper into stability, focusing first on covalent bonds. What determines their strength?
Well, fundamentally, covalent bonds form because the resulting molecule has lower potential energy than the separated atoms did. Energy is released when the bond forms.
So bond formation is exothermic.
Yes. And conversely, breaking a chemical bond always requires energy input. It's an endothermic process.
Okay, and we measure this strength using bond enthalpy.
Right. Bond enthalpy, or bond energy, is the enthalpy change required to break 1 mole of a specific type of bond in the gaseous state. For example, the HH bond enthalpy is the energy needed to turn 1 mole of H2 gas into 2 moles of H atoms.
And these values are specific to the type of bond, like CH versus CAC.
Yes. And generally, triple bonds are stronger, higher bond enthalpy than double bonds, which are stronger than single bonds between the same 2 atoms. Also, for molecules with multiple identical bonds, like the 4 CH bonds in methane, CH4, we often use average bond enthalpies because breaking the first bond might take slightly different energy than breaking the last one.
Okay, average values for polyatomic molecules. Can we use these bond enthalpies to estimate reaction enthalpies similar to using 80 HF degree values?
We can. It's another useful estimation method, especially good for reactions involving only gaseous substances where intermolecular forces aren't a big factor.
How does that calculation work? Is it products minus reactants again?
This is where you need to be careful. It's the other way around for bond enthalpies. Think about what happens in a reaction. You have to put energy in to break the bonds of the reactants, and you get energy out when the bonds in the products are formed.
Okay, energy in to break, energy out when forming.
So the estimated H degrees Rxn is the sum of the bond enthalpies of all bonds broken in the reactants minus the sum of the bond enthalpies of all bonds formed in the products. It's essentially energy input, energy released.
Remember, reactantstoffes, Bock minus make. Provides a good estimate, you say.
Yeah, it's usually a decent estimate, but it's not typically as accurate as using the standard enthalpies of formation, partly because it uses average bond values and ignores intermolecular forces. But it's conceptually very useful for understanding why some reactions release energy and others require it.
Makes sense. Okay, that covers covalent molecules. What about the stability of ionic solids like salt? They aren't discrete molecules.
Right. Ionic compounds form crystal lattices vast, repeating 3D arrays of positive and negative ions held together by strong electrostatic forces. Their stability isn't really about individual bond enthalpies, but about the overall stability of this lattice structure.
And we measure that stability using lattice energy.
Yes. Lattice energy is formally defined as the energy change required to completely separate 1 mole of a solid ionic compound into its constituent ions in the gaseous phase. For example, taking solid NaCl and turning it into NO plus gas ions and Cl gas ions.
That sounds like something you can't easily measure directly in a lab. How do you separate salt into gas phase ions?
You typically can't measure it directly. This is where we bring Hess's law back in a very clever application called the Born-Haber cycle.
Born-Haber cycle. Okay, how does that work?
It's brilliant, really. It breaks down the formation of an ionic solid from its elements, which is measurable, that's the standard enthalpy of formation, HF degrees, into a series of hypothetical individual steps whose energy changes we do know or can measure.
Like what kind of steps?
Okay, imagine forming NaCl from solid nonmetal and Cl2 gas. The Born-Haber cycle includes steps like 1. Turning solid Na into gaseous Na atoms, enthalpy of sublimation. 2. Breaking the Cl-Cl bond in Cl2 gas to get Cl atoms, bonds enthalpy. 3. Removing an electron from gaseous Na atoms to form Na plus ions, ionization energy. 4. Adding an electron to gaseous Cl atoms to form Cl ions, electron affinity. 5. Finally, bringing the gaseous Na+ and Cl ions together to form the solid NaCl lattice. This step is the negative of the lattice energy.
Whoa. Okay, so you have the AHF degrees for the overall formation. And, the energies for sublimation, bond breaking, ionization, electron affinity.
Right, since the overall enthalpy change must be the sum of the steps, Hess's law, the only unknown value in that cycle is the lattice energy, so you can calculate it by difference.
That's incredibly elegant. Using a cycle of known energy changes to find the one unknown, unmeasurable energy changes the lattice energy.
Exactly. It beautifully connects concepts like ionization energy, electron affinity, bond enthalpy, and sublimation energy all together through Hess's law to quantify the stability of the ionic lattice.
And ultimately, these fundamental differences in bonding strong lattices in ionic compounds versus discrete molecules with weaker intermolecular forces in covalent compounds explain their big differences in properties, right?
Absolutely. The strong electrostatic forces in ionic lattices lead to high melting points, hardness, brittleness. They tend to be solids at room temperature. Covalent compounds, especially molecular ones, often have much weaker forces between molecules, leading to lower melting and boiling points, often liquids or gases. It all ties back to the nature and strength of the bonding and the energy involved.
Wow, what a journey. We've really covered a lot of ground, from the basics of heat flow to these quite sophisticated cycles.
We certainly have. We've gone from defining the system and surroundings through exothermic and endothermic processes, the first law, enthalpy calorimetry, all the way to Hess's law, standard enthalpies of formation, bond energies, and even the Born-Haber cycle.
It really shows how chemists piece together different concepts and measurement techniques to understand the energy that drives chemical change.
It does. We've seen how energy is conserved, how its flow dictates whether something feels hot or cold, and how these clever indirect methods, like Hess's law and the Born-Haber cycle, let us figure out energy changes we can't measure directly. It's like detective work sometimes.
So, thinking about all this, what's the final takeaway for you, the listener? Well, next time you feel the warmth from a campfire or see condensation form on a cold glass, maybe think about the energy flowing. You're witnessing thermodynamics in action.
Right. Every chemical reaction, every physical change around you is part of this constant, intricate dance of energy. And maybe take it one step further. How could a deeper understanding of these energy changes, knowing precisely how much energy is released or required, help us?
How could it help us design, maybe, more efficient fuels, or new materials for batteries, or even understand biological processes better?
Exactly. Thinking about energy transformations on this fundamental level opens up huge possibilities. From material science to tackling global energy challenges, it all starts with these core principles of thermochemistry.
Keep exploring, keep asking questions, and keep digging into the why behind the what. You've just taken a deep dive into the fascinating world of energy and chemical reactions. We hope you gained some invaluable insights today.